Good afternoon, everyone. I'm Roman Skurikhin. My scientific advisor is Sergey Efter, and I'll present our findings about solvability of equation y prime equals y to the power m in the form of power series with integer coefficients. So let's first state the problem. We have differential equation y prime equals to y to the power m with initial condition y of 0 is a sub 0. And we are looking for solution in form of formal power series with integer coefficients. A couple of words about motivation for this problem. This equation can be easily solved as function over real numbers. You can just separate variables, integrate, and it gives you a result. But solvability for algebraic structure is not so trivial. For example, let's consider power series and case m equals 1. Then equation is just y prime equals y, and it gives recurrent formula for coefficients, and we can ultimately get a formula a sub k is a sub 0 divided by k factorial. But initial condition a sub 0 is some fixed integer that cannot be divisible by any factorial, so it can only be 0. And this yields only trivial solution where y equals 0. So for m equals 1, there is no non-trivial solution for our equation in the form of power series we are looking for. And for Lorentz series, in our case, where we only look for a part with negative powers, it was shown the solution exists only for case where m equals 2. So our task will be to look if there is non-trivial solution for power series with m greater than 1. To do so, first we'll need to come up with formula for coefficients. It can be easily achieved by derivating our equation k times. So we have our equation, y prime equals y to the power m, we differentiated k times, and it yields this formula after some simplification. Let's simplify it even more. First, let's introduce a equals m minus 1 and name our product term as ck. And also, let's substitute our initial condition. This yields the final formula for the coefficients of our power series. And we are looking for integer coefficients, so this fraction should be integer. So the upper term should be divisible by k factorial without any remainder. To check for this, we'll need the p-adic variation. This is simply the p-adic variation of some number n for prime p. It's just the highest power of this prime p that divides this number n. So, for example, if the number n is 12 and then p-adic variation for 2 is 2 because 2 to the power 2 divides 12. And p-adic variation for 3 is 1 because only first power of 3 divides 12. Using this notation, p-adic variation, we can rewrite our requirement. K factorial divides our term is just saying to say that p-adic variation for each prime of the k factorial is less or equal to the p-adic variation of same prime of our term. In other words, we can just say that if we consider factorization of this of k factorial and our term, then power of each prime in the factorization of k factorial should be less or equal than power such of same prime in the factorization of our term. Now we can define next lemmas. First lemma says that if there is a prime p that doesn't divide a that equals m minus 1, then p-adic variation of this prime for ck is greater or equal than p-adic variation of this prime for k factorial. In other words, when we'll be dividing by k factorial, the division by such primes will be handled by term ck. And if p doesn't divide a that equals m to m minus 1, then p doesn't divide ck at all. So division by such primes should be handled by something else, meaning initial condition. Combining these two lemmas, it's possible to achieve the following theorem. That's our main result. So this is the main result. As I said, that the theorem says that if m is greater than 1, the necessary sufficient condition is that for existence of formal power series with initial coefficient is a solution for our equation y prime equals y to the power m is that initial condition is a sub 0 is divisible by all prime divisors of m minus 1. Okay, and as I said, corollary is that if we don't consider initial conditions, then there is solutions for any m greater than 1. And this contrasts with the result for Lorentz series. Okay, next slide. Do you see it?
Yes, slide 6.
Yes. Yeah, thank you. Okay, so let's now look at a couple of examples to see how theorem works. First recall the formula for the coefficient. Here I've wrote it down in completely expanded form so that we can use it in examples. Let's first look at the case m equals 2. In this case, theorems say that we should look at the prime divisors of m minus 1. This is 1, so no prime divisors. So the condition of theorem always holds. And let's look how it works. If we look at first coefficients, we see that division is completely handled by the product itself. So it will always be integer no matter the value of a sub 0. This actually shows that the case m equals 2 is special here because solution exists no matter the initial condition. Same as in the case of Lorentz series. And let's look on the next example, m equals 4. In this case, theorem says us to look at the prime divisors of m minus 1. This is 3. So we need to check whether initial condition a sub 0 is divisible by 3. Let's look why it's required. Here we're writing down first coefficients, and we see that division by all primes except 3 are handled by our product. By division by 3 is not handled by our product. So this means that this division should be handled by our initial condition, a sub 0, as theorem predicted. That's all. Here are references, and thank you for your attention. Any questions?
Thank you for your presentation. Quite profound results. Very interesting problem. Maybe someone of
I have a
our guests.
question.
Please.
May I ask a question, please?
Чути.
Yeah, I can hear you.
First of all, thank you for good English. And the second question is why this differential equation is interesting? Why you trying to solve it?
Okay, let me go back. So actually, I'm working on some a joint topic called the copolynomials, and how to solve different equations with copolynomials. And this was like first example. We wanted to check that how it works for a more simple case. And we expected actually different results. We expected it to be the same as for Lorentz series, but it happened that it's not the same. So it was like by accident found some non-trivial mass here, and so it's this will probably be like the first example for my future work about copolynomials, and this like why working with copolynomials can be non-trivial. So this is an example for it. Did I answer your question?
Yes, thank you. And I have a proposition. In fact, well, they say the Maple system can solve differential equations like this in a form of formal series, but up to now it works only with linear differential equation. So you can propose your theorem to Maple company to include this method into their system. Maybe they will be thankful for you. That is my proposition.
Thank you. So Interesting proposition, but I think it would probably require to at least generalize this equation a bit, because currently it's only very simple case is covered. I'm looking to generalize, but yeah.
Nevertheless, the maple system cannot solve this equation.
Okay.
In a formal power series, so formal series, so you can propose your services. Thank you.
Okay. I'll think about it. Thank you.
Any other question or propositions?
Do you have any result about this equation in model of copolynomial?
Actually, copolynomials is there is theorem that says that there is like p action between copolynomials and Lorentz series. So actually, this is a result for copolynomials. I actually hide this fact from the presentation to not introduce the term copolynomials, but actually this is the result for copolynomials.
Thank you. Any other questions? Seems not. Seems everyone's satisfied. Thank you, Roman.